Good morning, children. The other day I taught you about the applications of refraction. Two cases. Object kept in a denser medium viewed from a rarer medium. It appears to be raised. Means apparent depth will be smaller than the real depth. This case, object in a rarer medium when viewed from a denser medium, then it appears to be at a greater height, shifted up. Okay, so apparent depth will be greater than the real depth. Now they don't ask such general things. Now you see lot of questions here. Okay, lot of questions here. So it's like a coin kept in a vessel, not visible when seen. Coin we have done. A print appears to be raised when a glass slab is placed over it. Okay, then there will be this stick appears short and bent. So all these questions, you have the basic will be the same in the diagram. You just have to make. So if it is asked, stick appears bent and short. Okay, stick appears bent and short. Then how will you show? How will your diagram be? So you draw your beaker with water. Then you draw the original stick. Then you show the bent one. Okay, so this should be your object and this should be your image. This should be your object and this should be your image. Okay, so as usual, from the object draw two rays and bends away from the normal because it is denser to rarer. So don't forget the arrow marks. Many of you have not drawn. When this is extended backward, you won't have it till this, children. You'll have it somewhere here. Okay, your image will be formed here. Is it clear? Your image will be formed somewhere exactly above it, no? Yeah, that's why the stick appears. This is its original length, but this will be its new position. So it appears bent and short. So real depth, and then this is its apparent depth. Is it clear? Now suppose if it is asked, okay, when it is about the glass, a tank appears shallow than its actual depth. So in that case, you just draw a tank. You don't have to take any object. You just take from the base. Okay, and in the incident rays going from the base. Okay, it looks shallow means what? The depth, it will look as if it is less. Okay, so from the actual base, you take two incident rays, normal, and you know that the apparent image will be here. So you can use another color pencil or something. So this is where your image should okay. So this is the real depth, this is the actual depth, but it will appear as if it is here. The base will not be here, it will look as if the base is here, so it looks shallower. Okay, so the same concept will be the same, but the questions can be asked in different way. Person's leg appears to be short when standing on a tank. So you can take a leg, okay, like this itself. Same diagram if you draw also, it's fine. Okay, appear to be short. Okay, so maybe if you can draw it little bent like this, that will be fine. Okay, instead of like this, you just draw like this. Okay, if you want, you put the feet also, but the basic diagram will be the same. And same way for this, I gave you one example. Fish inside water looks at a bird on a tree. The bird appears raised. Okay, show it by a ray diagram, then you have to draw it. Okay, so these kind of questions and numericals. So this is what comes from this part. Now let's go to the D part. critical angle and total internal reflection. Now, this is the most important part in the whole chapter, I would say. Okay, one question is for sure going to come from this. Okay, 4, 5, even 5 to 6 mark question comes from this, and so make sure you understand the concept clearly. Now, let's take a light ray traveling from a denser medium to rarer medium. It's traveling from a denser to a rarer medium. Okay, so this was the light ray. This is the normal. Now you know when it goes from denser to rarer, how it bends. It bends away from the normal. It bends away from the normal and goes like this. Now this is our angle of incidence and this is our angle of refraction. Angle of incidence and angle of refraction. Okay. Now what I'm going to do, I'm going to increase the angle of incidence. I'm going to increase the angle of incidence. So what will happen is, as I increase the angle of incidence, means I shift the ray like this. I shift the ray from here to here. Okay. So my angle I has increased. Then angle R will also increase. Angle R will also increase. Means the ray keeps shifting here. So as I shift this ray here, this ray will also keep shifting here. And at one point, this ray will fall exactly on this surface of separation. This angle keeps on increasing, and for one particular angle of incidence, for this particular angle of incidence, the refracted ray is falling on the surface of separation, or I can say angle of refraction is 90 degree. Angle of refraction is 90 degree. Now this angle is given a special name, okay, called critical angle. Critical angle. Critical angle. Okay, it is the angle of incidence for which angle of refraction is 90 degree, or you can say the refracted ray falls on the surface of separation. Anyway, you can say. Hope you have understood till this. Usually we take this and bends away from the normal. Now as I keep increasing the angle of incidence, the angle of refraction also keeps increasing, and there comes a point where this line will fall on this surface of separation. Now that angle of incidence for which angle of refraction is 90 degree, it's given a special name called IC. It's given a special name called IC. Now, if I further increase the angle of incidence, okay, that is, in this case, my I is greater than IC. The second case, I was equal to IC. Third case, I is greater than IC. Okay, at an angle greater than IC. Now, what will happen is, this ray, now as you know, from here it came here. Now it will bend and it will come inside. And it will become what? Reflected ray. Yes. This ray, when the angle of incidence is above critical angle, the ray will be totally reflected and come into the same medium. This angle will be the same as what you get here, angle R. And this phenomena is called total internal reflection. Total internal reflection. Okay, we go into it later. So, we have three cases. Angle of incidence. So, case 1, case 2, case 3. Case 1, angle of incidence less than critical angle. So, what will happen? Your incident ray will just bend away from the normal. And this is your angle I and this is your angle R. This is case 1. Case 2. What is your case 2? I is equal to IC. how the diagram will be. And remember, this should be always from denser to rarer. Now this phenomena cannot happen when the ray is going to come from rarer to denser. If the incident ray is coming from rarer entering into denser, this is not possible at all. Remember that. This is only possible when ray travels from denser to rarer. Now case 2, I is equal to IC. In that case, what will happen? My ray, if this I is less than IC, here I is equal to IC, then what will happen? My refracted ray will go like this and my angle of refraction will be 90 degree. And then come to case 3, that is angle I greater than IC. Angle I greater than IC. So how will my diagram go? So at this point, normal. So this is I greater than IC. I greater than IC, and the ray is going to be totally internally reflected. Means you have to draw like how you draw reflection. This angle should be same as this angle. Okay, this angle should be same as this angle, and it will undergo total internal reflection. This is called refracted through 90 degree, and this is ordinary refraction. It's like normal refraction. This is called refracted through 90 degree, and this is called total internal reflection. So these are the 3 cases here given: case 1, case 2, case 3. Now in all these diagrams, I have not drawn this reflected ray. I told you before itself, usually when refraction takes place, 95% of the ray will be refracted, 5% ray will be reflected. Okay, so it's not necessary to show this every time. In your book here shown, that's why. Okay, otherwise even if you draw only this, it's fine. Okay, reflected ray you leave, incident ray, refracted ray. This is for I less than C. He has taken as C, you can take IC or whatever it is. Incident ray bends away from the normal. Then case 2, I is equal to C. Okay, IC or C, critical angle, equal to the critical angle. Angle of refraction becomes 90. So this will be a diagram, leave of reflected ray. And then come to case 3, I greater than C or IC. No refracted ray is obtained and the incident ray is totally reflected as OC. Okay, so this is what will happen, and this phenomena is called total internal reflection, about which we are going to see in detail in this chapter, and it has lots of applications and all that. Okay, hope you have got it, children. From this we are going to get 2 definitions. One is definition of critical angle. These are the 2 new terms for you. One is critical angle and the other one is total internal reflection. So then we have to define these 2, critical angle and total internal reflection. Now see the definition of critical angle. Okay, this is the definition. Define: critical angle is the angle of incidence in the denser medium corresponding to which angle of refraction in the rarer medium is 90 degree. Angle of incidence in the denser medium corresponding to which angle of refraction in the rarer medium is 90 degree. That's the definition of critical angle. And then you have definition of total internal reflection here. Again, this is also a definition. When a ray of light traveling in a denser medium is incident at the surface of a rarer medium at an angle of incidence greater than critical angle. So this definition will have many parts. Traveling in a denser medium incident at the surface of a rarer medium, that's the first point. At an angle of incidence greater than critical angle for a pair of media, that's the second point. The ray is totally reflected back into the denser medium, and this phenomena is called total internal reflection. So this definition should have 3 points. Don't forget that. Ray should be traveling from denser to rarer. Okay, ray traveling in denser, incident on a rarer medium at an angle of incidence greater than critical angle, then the ray will be totally reflected back into the denser medium. This phenomena is called total internal reflection. Okay, so we got the definition, 2 definitions. Now little more about this critical angle. Now critical angle is, so this is the case, right? Case 2, when angle of refraction is 90 degree, I is called IC. I is called critical angle. Yeah. Okay, children. So let's study in detail the case 2 alone, because the critical angle comes here only. Okay. So let's take the denser medium to be water and rarer medium to be air. So incident ray is coming from denser medium entering into a rarer medium. So this is what is happening. So if you remember Snell's law, what does Snell's law say? Refractive index is equal to sine of angle of incidence upon sine of angle of refraction. Now, refractive index, always when you find refractive index, it will be of this medium, the medium into which it is going, with respect to the medium from where it is coming. So, refractive index of air with respect to water. Refractive index of air with respect to water will be sine, in this case I will be equal to IC and R will be 90 degree. So, sine 90 degree. So, my refractive index of air with respect to water will be, the value of sine 90 is 1. So, sine IC by 1. So, refractive index of air with respect to water will be sine IC. Now, this is the relationship between refractive index and critical angle. But usually when we say refractive index, we always say the refractive index of denser medium with respect to rarer medium. Okay. Water with respect to air. Now, will be 1 by sine IC. Principle of reversibility. Okay. So, if refractive index of air with respect to water is sine IC, refractive index of water with respect to air will be 1 by sine IC. 1 by sine is cosec. So, cosec IC. So, this is another. Air with respect to water will be sine. Water with respect to air is cosec. Okay. So, if you don't understand, just remember these two. That's enough. Okay. Don't break your head. So, by knowing the refractive index, we can know the critical angle. Okay. That's the main conclusion. By knowing the refractive index of a medium, we can find the critical angle. Okay. We'll use mainly this because the refractive index is always of a denser medium with respect to a rarer medium. Okay. So, refractive index of glass, if you remember, with respect to air, okay, is equal to 3 by 2, 1.5. I told you to remember these three refractive indices, if you remember. Okay, air is 1, vacuum is 1, water is 1.33. Okay, that will be 4 by 3, 4 upon 3 if I take it in fraction. And ordinary glass 1.5, that will be 3 by 2. Diamond 2.4. Okay, so in case of glass, refractive index of glass with respect to air is 3 by 2. That means cosec IC. For glass, cosec IC will be equal to 3 by 2. Now, if you see in the cosecant table and see for which value it is 3 by 2, IC comes out to be 42 degree. Cosecant of 42 is 1.5. So, the conclusion is critical angle for glass air interface is 42 degree. Okay, same way for diamond, for water, refractive index is 1.33 and 49 degree you will have. So, the conclusion is critical angle of water is, glass is 42 degree, water is 49 degree. So, there is a table and as usual you just remember these three: water, glass and diamond. Water 49, glass 42 and diamond 25 degree Celsius. Now, factors affecting critical angle. Two factors: color or wavelength, temperature. Again, both are directly proportional. More the wavelength, more the critical angle. More the temperature, more the critical angle. Okay, you don't have to know the definition, means explanation, just remember they are directly proportional. Now, so as I told you, we are going to focus mainly on the case 3. We will be focusing mainly on case 3, that is total internal reflection. So, whenever angle of incidence was is greater than critical angle, then the ray will be totally internally reflected into the same medium, and this angle will be equal to this angle. This is called total internal reflection. So definition we have done. Next is conditions for total internal reflection. What are the two conditions for total internal reflection? First thing, light ray must travel from denser to rarer. If it travels from rarer to denser, this phenomena cannot take place. The second one, angle of incidence must be greater than the critical angle. These are the two conditions. This also they ask often. Please study it properly. Now, what is happening here is like ordinary reflection. Okay, ray going bouncing back into the same medium. Okay, so this case is like ordinary reflection. So instead of mirror, we can use, by taking angle of incidence greater than critical angle, this particular, if it is suppose glass, okay, glass air interface or something, if it is a glass, take that it's a glass, I can use this to be, instead of mirror, I can use a glass block, and that will also behave the same way like a mirror. Now, why do we prefer this? Now, there's one great advantage of this reflection when compared to the ordinary reflection by mirror. This reflection is 100%. In the sense, all the reflected ray is completely, all the incident ray is completely, this is 100% reflection. No energy gets absorbed in the mirror. In mirror reflection, if I take a mirror, they say at least 5% or 3 to 5% gets absorbed in the medium. So out of this 100, only maybe 97 or 98, 95 to 97 percentage is only coming as reflected ray. So that way this is much better than this. So in many examples, the mirror will be replaced by a glass block or something, but the condition that they have to maintain is angle of incidence should be greater than critical angle. Okay, so this is what is given in this note. In the process of total internal reflection, 100% energy of light is reflected back. No other device such as plane mirror produces 100% reflection. Why? Due to absorption and refraction of some part of light. So due to this property, phenomena is used in construction of periscope, binocular and certain types of camera, which we'll be seeing later. Okay, this will be the last thing for today. Now, all the three diagrams, okay, all the three diagrams I can draw in a single, we can show it in a single diagram also. Okay, so how are we going to show that? So you take a long surface and you take a normal maybe, okay, a line like this. From this, let it be the object or incident ray. So draw three rays, 1, 2 and 3. Please use scale and pencil, children, so that you get proper one. Okay, now the first case, I less than IC. Second case, I equal to IC. And third case, I greater than IC. Now let's draw the refracted ray. For this case, I less than IC, ordinary refraction. So your refracted ray will be like this. For second case, I equal to IC, your refracted ray. So you darken it, okay? This line you have to darken it and show that angle R is 90 degree. And third case, I greater than IC, the ray will be totally internally reflected at the same angle. So here total internal reflection will happen. Is it clear? So in a single diagram, we have shown all the three. So this is ordinary refraction, this is refraction through 90 degree, and this is total internal reflection. So this is the diagram that gives all the three together. Okay, I have not shown this reflected ray, it's fine. Okay, so with this I'll stop for today, and the homework will be page 101, question number 14. Okay, this is water to air, okay, but the same type. Question number 14. 15, do it in book itself. Book itself. 15, okay? Because answers are given there, but I want you to go through it. This is how the questions will come, so you'll get an idea. Okay, so 14, 15 in book itself, 16 again in notebook. Okay, glass air interface. So they're asking you to draw 3 rays, PA, PB, PC. So something like this. So you take it as P, PA, PB and PC. And they're telling you to take a glass block. Okay, so you take it like a glass block. But that's all. This is glass and this is air. This is what will happen. Okay, then you have to do 17 also. Okay, leave of 20. I have not yet reached here. So basically in notebook you will do 14, 16 and 17. This you will do in book itself. I'm sure the homework is clear. Please finish it. Send it to me by tomorrow. Thank you, children.